Hi everybody, Mr. Lee here. In this video we are going to go over the RAMP post lab. Alright, let's begin. Okay, so if you remember from the RAMP post lab, we all got data and I probably gave you the perfect set of data. And with that perfect set of data, we got a graph that looked something like this. Okay, so if you're at home taking notes, be sure to just give me a quick sketch of this. So we have a position versus time graph where position is in meters and time is, of course, in seconds. And we always need a good title. Because this is a sketch, we don't have to do plot points. But we did get a line that looked something like that. Okay, now from there, I asked you, how can we linearize it? Now, this is probably the first time we or you have linearized in your science classes, and that's why I gave you this worksheet to really help us out. Now, based off of this worksheet, all you have to do is to see which graph, looks like your graph shape. All right. So in this case, right, our upwards parabola looks like this graph right there. Now, if we take a look at that graph, this worksheet tells us everything that we need to know about this variable. So the y-axis, so for us this is position, is proportional to the square of time. Okay. Now, the worksheet also shows us how we can now linearize this graph. Now, linearizing simply means that you take your graph, you somehow adjust the data set mathematically so that you have a straight line. Now, the reason why we want a straight line or a linear line is it makes understanding and reading the graphs a lot easier for us as scientists. Okay, so if we take a look at the worksheet here, it says we have to graph y versus x squared. All right, so I'm going to do that over here, where our y-axis is still x. Okay, we didn't adjust that yet, but our x-axis is now x squared. So this will now be time squared. Now, it's important to know that you also have to square your units. So if we take a look here, our new graph title will be x versus t squared. Ta-da! All right, now when we did that with the perfect set of data and we graphed it, we got a linear line. And that's why we call it linearization. Okay, and so from here, because we have a linear line, we can now use this wording, and that wording will hold true for the variable. So we can say, as time squared increases, position increases proportionally. Or another way to write it out is that position is directly proportional to time squared. All right. Now, from the perfect set of data, we found that the slope for this graph gave us a value of 3. Okay, now if you remember, for slope is a rise over run, and our rise units are meters, and our run units are seconds squared. So our slope would be 3 meters per second squared. Okay. Now, it's important for us to really verbalize what's happening at this moment and try to connect it with the lab itself. Okay. And the reason why I want to do this is to showcase exactly like what's going on with this situation. So if you remember from the buggy lab, in order to verbalize the slope, we always went with the denominator unit first. We would say for every 1 second squared, the cart moved 3 meters down the ramp when it was at an angle. Okay, so what I'm going to do now is I want to highlight the parts I want to really showcase. Okay, this is for every 1 second squared, the cart moved 3 meters down. Now, if you're thinking to yourself, what the heck does that mean? That's very good. You should be thinking to yourself, what the heck does that mean, right? What is exactly a 1 second squared? No one really talks about the time in terms of second squared, and that's very important for you to internalize in your head, because that will pop up again and we will clarify exactly what that means in the future. Okay, now with these graphs, it's important to have a general math equation. So this is my general math equation. And what I'm going to do for this general math equation, I'm going to get it from our linearized graph. So if you remember our general math equation, we always use the point slope formula. So y equals mx plus b. We know that our y-axis was x, okay, or position. Our slope was 3 meters per second squared. Okay, I'm just going to put my units in parentheses, and our x-axis was time squared, and our y-intercept was just 0, right? So if I were to write our general math equation, I would just write it as x is equal to 3t squared. Let's highlight that because that's going to be very important. Now, if you have taken a math class where you have plotted points where it's like y equals x squared, you know that the plot that you will always get is this upwards parabola, right? And so what this shows us is that the formula for this position versus time graph, right? This graph, the formula for this graph is x is equal to 3t squared. And that's not a coincidence, okay? That was on purpose, and that was intentful, right? The general math equation for a linearized graph is the equation for the non-linearized version, okay? So what that is showing us is that it is the same data set, right? It is the same lab, okay? It is showing us the same exact thing. All right, wonderful. And I hope you thought that was really cool. So let's discuss this idea of meters per second squared, right? So what is meters per second squared? Now, if you've taken a physics course before, maybe in middle school and your other classes, you might already know what meters per second squared is. But up until this point, we've never discussed what meters per second squared really means. But it's important. It's very important for us to know this is not speed. Okay, it is not speed, and it's definitely not velocity, because the units for those were both meters per second. All right, yeah, let's definitely highlight this. This right here is one of the most common pitfalls for many of the physics students. Okay, they try to make connections, and in those connections, they're like, oh, meters per second, that's close enough to meters per second squared. It must mean the same thing. But I need you to know and understand that it is definitely not the same thing. Okay, so are we going to define it? Yeah, later, but not for this post lab, okay? Because we didn't define it yet, and that's fine. So what I want us to do now is I want us to create another representation, another model for this whole idea of our general math equation, x is equal to 3t squared, using a table. Okay. Now the reason why I want to do this is, even though I gave you like the data set before, it gets like really cool. We're actually diving into the minds of Galileo. Way back in history, when he did this lab, he didn't have like timers. He actually built his own timer. They were called water clocks, and so yeah, he actually invented a clock or a method to do a ramp lab before your digital timers were even around. All right, so let's actually reverse that. So we'll call this time here, and we'll call this time, of course, in seconds, and this will be position, of course, in meters. All right, so at the 0th second, we were at the 0th position. After 1 second, according to this mathematical formula, it should be 3, 2, this should be 12, 3, this should be 27, and 4, this should be 48, and 5, this should be 75. Now, this should look familiar because this is the perfect data set that I gave you. All right, now let's really dissect this down. So according to this formula, there's a couple of things that we can do mathematically. Okay, so all we did is we plugged in the time value and we got the x value. But what I want to do now is I want to go in and divide out 3 from all my x values. So I'm going to write that out. Divide 3 from position values. Okay, now bear with me here. I'm going to do it right in the next column, and I'll do it in a different color so that we can see it. All right, so 0 divided by 3 is just 0. 3 divided by 3 is 1. 12 divided by 3 is 4. 27 divided by 3 is 9. 48 divided by 3 is 16. 75 divided by 3 is 25. Okay, so from there, let's actually dive into what Galileo found. He saw, watch what I do, he saw that this number and this number, 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 this number and this number have a very special relationship. Okay, so 0 squared is 0, 1 squared is 1, 2 squared is 4. Whoa, 3 squared is 9, 4 squared is 16, 5 squared is 25. So what we did essentially is get that general math formula, and we found the relationship again. Okay, that relationship is popping up over and over again, where position is directly proportional to the time squared. Okay, this is the perfect squares. Okay, and this is something that is very unique to our world, and this is something that we will be seeing many times. So if you see that relationship, know that we have a perfect square relationship. All right, now what that finally brings us to is our final closing statement. Okay, what did all of this mean? Okay, why are we doing this? So this shows us what we are going to call the law of falling bodies. Okay, now yes, technically we were on a ramp and we were rolling down the ramp, but if you think about it, right, if we weren't on a ramp but rather like a flat surface, we wouldn't be going anywhere. And because we were on a ramp, we were rolling down, and we, in terms of physics, we call that a falling body. Okay, and I'm just going to put in parentheses here. If you often hear me refer to this law as the ramp lab law, okay, that's just a way for me to make sure that you remember that this activity that we did and the relationship that we got. All right, and this law shows us when objects speed up. Okay, now I want you to notice here that I am using the vocabulary term speed. However, we're not talking about speed directly. We are calling it speeding up, and this is the phrase as a whole. So the law of falling bodies is the law of objects speeding up. All right, and that law for us is defined as x is equal to k t squared, where k is a constant. Okay, and for our perfect data set, our k was 3 meters per second squared. If we were to increase the angle of the ramp, that 3 would go up. If we decrease the angle of the ramp, the 3 would go down. But it's the important idea here is that k is just a number, okay, and that number we get from graphical analysis and from getting data. And most importantly, x is directly proportional to t squared. All right, so that is a nice little summation of our entire ramp lab. All right, I'll see you next time. Bye-bye.